let's take a look at this molecule here, and let's write the name, the molecular formula, the empirical formula, let's find the molecular mass, and let's see what is the mass of .37 moles of this stuff. Okay, so we've got 3, 4, it's like 5 different parts to this problem. And while we're at it, let's just write the complete combustion equation. So notice there are no double or single bonds here. That means that the end is going to end in ANE. Now, this is a cyclic structure. It is a cycle. We've got 1, 2, 3, 4, 5, 6 carbons. So I'm going to have to say, because it's 6, I say hex. So this means 6 single bonds. But I have to show that it is in a cycle. So I'm going to say cyclohexane. Now, remember that when you have a cyclic structure, you're going to begin your numbering at the group which comes first alphabetically. So this one is a methyl, and this one, 1, 2, 3, is going to be a propyl. M comes before P, so that means that I'm going to call this my number 1 carbon. The second part of this is we have to make a decision. Do we number this way, 1, 2, 3, 4, 5, or do we number this way, 1, 2, 3? And the rule is that you're going to number it in such a way that your next substituent will be the lowest number. So if we number this way, our propyl group is going to be at the 3 position. If we numbered it the other way, 1, 2, 3, 4, 5, the propyl group would be at the 5th position. So we want to keep it at the lowest group possible. So we're going to have 1 methyl, comma, 3 propyl cyclohexane. So this is our first writing the name. Now let's go write the molecular formula. Remember, you've got these 6 carbons. This makes 7, 8, 9, 10. So I have C10. Our hydrogens. This carbon right here has 1, 2, 3 bonds, so I can put a hydrogen here to make it 4. This one has 2 bonds, so I can put 2 hydrogens on it. This one has 1, 2, 3 bonds, so I can put a hydrogen right here. 2 bonds, so I can put 2 hydrogens to make 4. 2 hydrogens and 2 hydrogens. So for hydrogens, we've got 3 right here. This makes 4, 5, 6, 7, 8, 9, 10, 11, and this is 12, 13, 14, 15, 16, 17, and that would be 20. I'm going to recount that because I don't want to make a dumb mistake. I'm just going to count it a different way. So 3, 5, 7, 8, 9, 10, 13, 14, 15, 16, 17, 18, 19, 20. So C10H20. This would be the molecular formula. Now, the empirical formula is going to be the lowest ratio. Both of them can be divided by 10. So the molecular formula is C10H20, but the empirical formula is going to be a CH2. That just means for every one of these, you've got 2 of these. Now, the empirical formula is mainly a lab type of thing. When we do lab analysis, we're finding a ratio of one thing to another thing. This is what we're going to use most of the time. So let's determine what the molecular mass is. In this case, we've got 10 carbons times 12 grams per mole. It's 120 grams per mole. We've got 20 hydrogens times 1 grams per mole gives me 20 grams per mole. Add them together, total gram molecular weight 140 grams per mole. Okay, so that's my molecular mass, my molecular weight. Then we're asked a problem, what is the mass of 0.37 moles? So if we take this, we start with what we're given, 0.37 moles. Put it over 1 so that we have a top and a bottom. We want to end up with grams because the question asks us what is the mass. So we're going to put this so that we end up with grams. That means we're going to leave it. We're not going to flip it. So it's 140 grams per mole. End up with grams. 0.37 times 140. I got 51.8 grams. Okay, we wanted to take this one step further. We wanted to get the complete combustion equation for this. So I'm going to turn my page here. The complete combustion equation, we've got C10H20. Remember, combustion needs oxygen, and when we have 100% complete combustion, we get carbon dioxide and water vapor. So again, I'm going to use my pencil. I'm going to start with balancing my carbons. I'm going to put a 1 coefficient here. I've got 10 carbons, so I'm going to say 10 in front of that. 20 hydrogens would be a 10 in front of there. That gives me 10 times 2 is 20 oxygens here and 10 here, for a total of 30 oxygens on this side. I would have to put a 15 in front of that, give me 30. So if you think of it in terms of burning something, if you were to burn 1 unit of this, you would require 15 units of oxygen out of the air and 10 units of carbon dioxide would be put into the air. We might as well take it one step farther than that and turn this into a little stoichiometry problem, which we're getting ready to do a lab on this. Not necessarily with this particular compound, but let's assume that we've got 2.5 moles of C10H20. And we want to know how much carbon dioxide are we putting into the air. So if we just look at our ratio here, we've got a 1 to 10 ratio as it's written. If we turn that into 2.5, we're basically, we can cross multiply and solve for x. However, your math teachers taught you to do ratios before, but I think it's easiest just to multiply by 10 and get 25 moles of carbon dioxide put into the air. In case you didn't quite see that, I just turned it into a ratio problem and solve for x. So x equals 10 times 2.5 or 25. This will not be on the test that you have tomorrow, but we will be doing this and a little bit more in the lab.